Okay, so welcome everybody once more to the official IAU G2 online conference series. This is, as usual, about massive star, and today we have a seminar covering a topic which we have not touched yet in this conference series, star formation. So this will be very interesting. It's hence with great pleasure that I want to introduce our speaker today, James Chibueze. James is presently a distinguished professor of astrophysics at the University of South Africa. He obtained his PhD in radio astronomy from Kagoshima University in Japan in March 2013. After that, he worked for the East Asian ALMA Regional Center at the National Astronomical Observatory of Japan, also at the South African Radio Astronomy Observatory, and in the last year in the Northwest University in South Africa. His research interest is on high-resolution radio interferometric observation on high-mass star-forming regions and radio galaxies. And he also serves currently in the IAU Executive Committee as one of the vice-presidents, and is also co-director of the Pan-African School for Emerging Astronomer, and is the co-founder of the Global Emerging Radio Astronomy Foundation. So many interesting things here. So thank you very much, James, for accepting our invitation to talk about your recent research. And whenever you want, the floor is yours.
Thank you very much, Sergio, for the introduction, and thanks everyone for joining. I would plead to deviate a bit from what you used to hear from this seminar and talk about something slightly different, focusing more on radio images or radio observational results. But there will be some things in infrared, not so much in optical. So what I'll try to do in the course of my presentation is to reconstruct what we think or what we currently know as the evolutionary sequence of high mass stars from the early stages to a bit more advanced stage. I'll talk a bit about supernova explosions towards the end of my talk. Okay, so keep in mind that the basis of my talk will be mostly to show some of the fundamentals and then to put out some of the constraints that we have regarding understanding high mass star formation and a couple of questions, some of them still not completely answered regarding high mass stars. And then I will go through what I consider to be multi-wavelength. In some cases, it's multi-wavelength only within the radio band. In other cases, you would see some infrared images that we use to do comparison. And then I know there are still more missing links, but what I will try to present to you is what I think is an updated view of what we understand now as the evolutionary sequence of massive stars. So before I go in, here are a few radio fundamentals, just in case there are people who haven't been introduced to radio astronomy before. Essentially, if you look at the EM spectrum, when we talk about radio, we are focusing more on the long wavelength parts of the electromagnetic spectrum, covering the millimeter all the way to the short centimeter microwave and to very, very long few meter microwave emission. However, of course, you probably do know that if you have a wavelength longer than 30 meters, it's impossible for us to receive such signal from the ground because the ionosphere is very opaque, completely bounces back all signals above 30 meters. So 30 meters and below, we can pick up from the ground, and we do have radio instruments that do observations in those bands. What exactly do we observe? Well, we do two kinds of observation in radio. It could be continuum observation or spectral line observation. For continuum, if you are observing in millimeter band and picking up dust emission in millimeter band, you're mostly looking at things that come from black body or at least an approximate black body radiation. And when we talk about black body radiation, I think what will come to mind is the Planck's distribution function, with which if you plug in the temperature of a body, like in this case, the cosmic microwave background at 2.7 Kelvin into the Planck's distribution function for a range of frequencies, you can reconstruct the blackbody spectrum of the cosmic microwave background. Of course, this is dependent on the temperature of the body. You can do the same for human body, and you can pull out the spectrum. You do the same for the sun. You pull out the yellow part of the spectrum. If you put in temperatures that correspond to temperature of very massive stars that have surface temperatures of up to 100,000 Kelvin, you will reproduce this spectrum. So that is mostly what we look at in blackbody radiation, and this sort of radio emission can be picked up by telescopes and used for studies. The other kind that we look at is what you call free emission. The German word for free is Bremsstrahlung. I hope I pronounced that well, if there are Germans here. So typically what you see in free emission is it happens in a region where you have high enough temperatures to break hydrogen atom into proton and electrons. And of course, we usually consider the proton to be quite much more massive than the electrons, and therefore we consider the motion to be close to zero, or at least zero. You consider it to be stationary. The electrons, which are lighter in their mass, typically would travel at faster speed, and when they come close to a positively charged ion, the attraction force pull them closer, but not trap them. If it's completely trapped, it goes towards this side. It becomes a spectral line, but not an emission line, but an absorption line, because energy is sunk into the system. So we're not talking about absorption line. We're talking about deflection of the electron, not completely trapped. So the energy it has while it's approaching is energy 1. The energy it has after his part is bent is energy 2. The difference between these two energy is the radio waves that is giving out. And such emission we call free emission. You hear people in star formation talk a lot about H2 regions. H2 regions are essentially ionized regions that are giving out this free emission. The third one is the non-thermal process. The first two I mentioned has to do with the temperature of the body. You need some temperature to ionize hydrogen. You definitely need temperatures to warm up dust or anything else in order to generate the blackbody spectrum. However, the third continuum here is completely non-thermal, has nothing to do with the temperature of the body. However, you simply need to have a relativistic electron. That's electron moving at speed, very close to the speed of light, getting coupled in magnetic field. And each time it makes a spin, there is an acceleration of the particle. Acceleration means a change in velocity. A change in velocity corresponds to change in energy. And the difference in the energy corresponds to the energy that is giving out. So knowing that these particles can carry a wide range of energies, therefore this emission is continuum, because wide range of energies means E is equal to h nu, okay? So it means a wide range of frequency. So it will cover a broad range of frequency on your receiver band. So essentially becoming broadband, which is what we call continuum emission. For the spectral line, you could get them as a result of vibration of molecules. In this case, let's assume this is water molecule. If you have a molecule that have atoms bonded to each other, the bond is not rigid. It almost acts like a spring, and it could vibrate. It could also rotate about an axis. In some cases, if it's a polar molecule. And these vibrational states and rotational states lead to emission of radio waves. And those radio waves, depending on which atom or molecule, happen at specific frequency. I'm sure there are lots of people with experience in spectroscopy. In radio, we also pick up lots, hundreds of thousands of spectral line, molecular line. Hydrogen is one popular line that we like a lot. It's the most abundant, that's neutral hydrogen. Remember, the ionized hydrogen is H2, neutral hydrogen is H1, and H1 happens as a result of a change in the spin direction of the electrons that is orbiting the positively charged nucleus of the atom of hydrogen. And that's quite cool. You can use this to do lots of calculations, determine a lot of properties of objects in the universe. The other one I'll mention a lot, I wouldn't go too deep in explaining. If you have more questions on this, you can ask me, are the masers. Masers are simply microwave equivalent of lasers. So laser is light amplification by stimulated emission of radiation. If you replace light with microwave, which is in the radio band, then you get masers. And we use this a lot in radio astronomy because they are super bright. And I'll show you why they are super bright. And most of them are very compact. So you can use very long baseline interferometry to determine positions using masers. And how do you pump masers? Essentially, particles in a molecule prefer to stay in lower energy state. We know that these energy states are quantized. So if they acquire energy and jump to higher energy levels, if you find any molecule with the particles in it having energies higher than that of the ground energy state, that is a very unstable state. And we call that in maser astronomy population inversion. So you essentially seeing inversion of population levels to be opposite to what you expect. What you expect is that there will be more particles or electrons at the lower energy states, but you find them at higher energy states. So if you have population inversion, then you're very likely to have a maser, because all you will need is a stimulant, this incoming incident photon, to come in, trigger all these particles at higher energy level to emit at exactly the same frequency as the maser line, and therefore come down to lower energy level. So what it means is the incoming photon is 1, but the observer is in this end. You find a beam of emission depending on the path length of the maser cloud, which is super cool. It means you can find star-forming regions, for example, at physical temperatures less than 50 Kelvin, but generating maser emissions that are in millions of Kelvin in terms of brightness temperatures. That is because of masing processes, because you can't explain that process with thermal emission. The object is not hot enough to generate emission with brightness temperature of 10,000 Kelvin or 1 million Kelvin. So you can only explain it with masers. So these are the fundamentals. I'll be pointing to dust continuum from ALMA. Just think about it as is a black body radiation. I'll talk about H2 regions, think about this. I'll mention some jets. We have seen synchrotron jets in star-forming regions. So it might be particles that are accelerated relativistically. I wouldn't mention a lot about H1, but I'll show quite a number of molecular line tracing outflows, and I'll show lots of masers also tracing a couple of gas kinematics around star-forming region. Okay, can everybody still hear me well?
Yeah.
Okay, good. So here is why I think high mass stars are quite interesting. Maybe that's why all of you study it. We know that they are very, very rare, well, compared to other stars. For example, if you're looking at stars that are less than like the red dwarfs, that makes up about 41% of the stars we know. If you go down to the dwarf stars, it's 28%. If you go down to stars about half the mass of the sun to exact mass of the sun, it's about 19%. But when you start going towards the massive stars, you drop very low. I mean, things come down to fractions, like 0.3% of the known stars, which is very, very small. But as rare as they are, they play a very crucial role in shaping the morphology. You all probably know this of their host galaxies. Both the chemical evolution, the chemical composition, the morphology of the galaxies are all interestingly shaped by massive stars. Here is a simulation that was recently made by Northwestern University Star Formation Group. I think is the most up-to-date. Previous simulations had just collapse systems where you don't consider the stellar wind or outflow that complicate the environment. But this has included some of these feedbacks, and I think it's cool. If you haven't seen it, you will see it right now. So you start with a giant molecular cloud. The color gradient just shows you that the densities are inhomogeneous. So if you put in heterogeneous systems, you can see subclouds in yellow, and you allow it to collapse gravitationally over time. And that's what you see. Of course, time here is in mega years, just to speed things up. And the scale here is about 10 parsecs in linear scale. So what you may have seen in the beginning is that the subclouds within the giant molecular cloud come together, collide, and slowly you could start seeing tiny, faint, long filamentary structure forming. And within the filamentary structures, you slowly start to see dense cores. And of course, in the dense cores, you start to see outflows, and the outflows are just so complex. Remember that these outflows are coming from rotating structures, so they tend to sometimes precess. And then the ejection is also episodic. You can find knots along the jet. So this makes Hymer star formation quite interesting because you can see many massive protostars forming close proximity to each other, and therefore makes the environment gorgeously beautiful, but extremely complex to study. But difficult things are interesting. It means you'll find new results. Cool. Okay, so just providing a few facts about Hymer stars. As I've shown, well, in this slide, they form in close proximity. That is point number 4 to each other. Therefore, the formation environment is extremely complex and sometimes fairly difficult to understand. The other problem we have with Hymer stars is from our solar system or from our sun to the position where these stars are located are significantly far away. We don't have Hymer stars 100 parsecs away. The nearest one is Orion, which is about 420 parsecs away. The second nearest one is Cepheus A, I think at 600 parsecs. The rest are between 800, just a few, 2 or 3 more around 800 parsecs. The rest are up to 1 kiloparsec away. And there are some on the other side of the Milky Way, just across the galactic center. So you have massive stars 15 kiloparsecs from our solar system. And we do have some parallax measurement with VLBI for some of these distances. So it's not kinematic distance, which may be ambiguous. Also, unlike the smaller stars, like our sun, which you probably can claim it will live up to 9 billion years, Hymer stars evolve super quickly, as you know. Within a few billion years, they can move through their evolutionary track and die in supernova explosion, leave a pulsar behind, or maybe sometimes form a black hole. However, they are very cool because they generate heavy elements, which is nice. So they literally play a key role in the chemical evolution of their host galaxies. Of course, they also shape the morphologies, and there are questions about Hymer stars that we do not have answers to. For example, why do massive stars continue to accrete even when they're already in the main sequence? And how do they gain their mass? How do you build a star that is 20 times the mass of our sun? And are there clues we can draw from observations regarding their evolutionary track, especially in the early stages? These are all useful. So if you have stars that play such a key role in shaping the chemical evolution of the host galaxies and also their structural and morphological evolution, then they must be very important, and we need to understand how they are born, how they evolve, and how they end their life. Okay, here is what I'll call a summary that I will now take sequentially to explain and show evidence of each of these stages. Remember, I said earlier on that you go from giant molecular cloud, which typically would not have homogeneously distributed densities of matter. Okay? So you have inhomogeneity, so it means there are subclouds within the giant cloud. And these subclouds will have differences in their masses, therefore gravity will kick in and they will pull each other together. And when they collide, they form filaments. And these filaments can be fairly clumpy and have some dense region that are quite extremely cold, I think sometimes between 10 and 20 Kelvin in temperature. So these filaments, we consider the formation of these cores as a process we call fragmentation. Will give rise to what you call massive dense core, prestellar core. At this stage, there is dust condensation, but there is no gas. So what you see at the top is just illustration of each of the evolutionary stage. At the bottom are observational evidence. Those who do infrared observation, I'm sure you've seen infrared dark cloud or infrared dark filaments. This is one example of G19.30. And within the dark filament, you could see cores that are already formed, probably already have some massive star. This is bright enough to probably be a compact or ultra-compact H2 region. However, before that stage, you have the prestellar core, which is the cold phase, where you have a dust condensation, which you can detect in millimeter dust continuum. However, if you try to look for the gas within this, you'll find a hole. The background is N2H plus gas, and there is no gas peak on top of the continuum peak. This is an evidence that this massive stellar core is still in pre-stellar phase. There is no star in it. There is no gas. Of course, over time, this will get, the density will increase, the temperature will warm up, and the molecules that are formed in the dust grains, frozen onto the dust grains, will be evaporated. Now you can detect lots of molecules like silicon oxide, which will trace outflowing gas, methyl cyanide, which would trace rotating disk structure or even rotating envelopes, Hessian, which would trace the high density material, methanol, which sometimes trace the disk, can also trace the shocked, depending on which of the transition you're looking at. It can trace the cavity walls of the outflow and so on. So this comes as a result of these molecules are formed in the cold phase, because at that time, when the dust grains are extremely cold, you have from simple molecules, you could form complex molecules. There are people more experienced in explaining how these form, but those low temperatures allow you to produce different kinds of molecule. However, when these things, the protostar warms up and become a hot core, it warms up it releases UV photon that warms up the dust, and then the dust, when it gets warmer, releases this gas, and we can detect them depending on the abundances or the column densities available. So that's the hot core phase, and we have examples indicated here. And over time, of course, the temperature becomes significantly warm, that you can now break hydrogen into proton and electron, and you can start to have free emission. At this stage, the ionized environment is still very small, about 0.01 parsec in size. So we call that hypercompact H2 region. Of course, this warm environment will continue to release energetic photons, and more of the region are ionized. It could get into classical, what we call classical ultra-compact H2 region. This form, the morphology in what we've seen in observation typically show cometry structure, where you have a bright head and a faint tail kind of morphologies. But that is cool. So it's ultra-compact H2 region. Typical size is larger than 10,000 AU or smaller than 10,000 AU. And of course, this will have neighbors because there are massive stars forming close proximity to each other. They'll continue to ionize and form this classical OB association with a larger size of ionized environment. And if you've seen Orion anytime, this is exactly what it looks like. Okay, there are a few new stages that is not included here, but been added here in the test, like things like accretion burst. We cannot pin it to any of these phases yet, but we think within these two phases, you have what we call accretion burst, which I will explain later. Okay, this is roughly what we know about HIMA star, but I would like to now take it one after the other and show evidence, observational proof for each one of them. The first one will be filaments. How do they form? Where do they come from? Well, going to Herschel, if any of you participated in building this project, I would say huge congratulations. This made significant impact in our understanding of HIMA star formation. And one of the things he told us is that filaments are ubiquitous. They're just everywhere. Wherever you look in the Milky Way, you find filaments, okay? And filaments are these nice elongated structures, high density structures. It's a bit brighter here. That has been found with Herschel. And in this case, this is the Cat-Paul Nebula. I've put in this picture taken by Kamino-san. Kamino was my professor in Kagoshima before he joined the ALMA project and moved to Chile. And he loved to do astrophotography. He took this picture. And here is a Cat-Paul Nebula. If you zoom in with better optical image, that's what you will see. If you observe this region with this, you'll find these nice filaments that you see in the cold dust environment. If you zoom into the bright spot and change the contrast a little bit, you'll find these nice filaments, but along the filaments, there are bright regions that you can consider dense clumps. And they're labeled I, N, this is I naught, and this is I. Sometimes these are classified. Papers refer to them as twin massive star forming region. And there is number 2, 3, 4, and 5. So yes, filaments are everywhere, but how do you form these filaments? Okay, here is one observational evidence that among other methods to form filaments, cloud-cloud collision might be one of the most effective ones to use to explain how filaments are formed. This is the brick. This source is called the brick. It's close to the galactic center. And if you observe it in optical and infrared, you find this nice arc-shaped infrared dark cloud or filaments. So what we did in 2014, was to pick out ALMA observation of this region and look at some of the molecular line. I think in this case, this was SO2. And here is the surface brightness distribution of the emission that we looked at. You can see it's a bit clumpy, but it does nicely reproduce the C shape. And to tell you that there could already be some level of star formation within this cloud, there is a position here where my cursor is, where I have labeled water masers, where we have detected water masers. And this kind of maser are collisionally pumped, so it could be that there is a shock environment around here, which is typically evidence of star formation. However, if you reconstruct the moment 1 and moment 2 maps, moment 1 is a velocity field, moment 2 is a velocity dispersion field. you find huge amount of velocity dispersion, also a huge gradient in the velocity field in the inner part of the arc. You see also a huge gradient in the velocity dispersion. So this can give us a clue. Of course, the shell structure here, which corresponds to this arc structure here, could tell you something about how this filament is formed. And if you try to model this and assume that you have two clouds colliding, then you can form these nice filaments. And of course, depending on the masses of the cloud or their sizes, the shape, the morphology of the filament could change. So in the case of this one, we think it came from the collision of a small cloud and a very large cloud. By the way, the simulation was done by Asai. Yeah. No, I think I forgot the Japanese name, but I can remember it later. So you have a small cloud and a big one, of course, having density discontinuities or inhomogeneous distribution, and they collide, okay? So the panels here just shows you the evolution of the collision, and over time you can form this arc shape, which we have. Well, if you flip this around, that is similar to the arc shape that we found. So somehow, numerical simulation could reproduce the morphology we see, and therefore we're convinced that cloud-cloud collision must be involved. However, to maintain the shape of the arc after a long time after collision, there might be need to plug in some magnetic field. I haven't seen any simulation that includes magnetic field, but we have seen examples where people think filaments are sustained by magnetic field lines. So there could be a combination of cloud-cloud collision and the impact of magnetic field to form filaments. I think from the results that we've seen from the Nanten telescope, from lots of the single dish observations, they've seen lots of evidences after we proposed this cloud-cloud collision. It started running cloud-cloud collision proposals as a way of forming various filamentary structures within the Milky Way, which is cool, in my opinion. Okay, so the first stage, filaments, we think they are formed by cloud-cloud collision, and there may be a role that magnetic field play in sustaining the filamentary morphology. So we go to the next thing, which is the prestellar cores. We think that prestellar cores come from fragmentation of the filaments that are formed. And by the way, I have just used filaments in a general sense to describe these long structures. But remember that if you stretch out your baseline now, I don't know how much you know about interferometry, but let me assume you have some idea, even if you don't fully understand it. Interferometry is doing observation with a number of radio telescopes simultaneously, and then your resolution is improved by a factor of the separation, by the separation of the two antennas as seen by the source, seen from the position of the source in the sky. So if your baseline is longer, you have higher resolution, and that means that you can start to resolve these filamentary structures to even tinier long filamentary structures, and we call those fibers. There has been lots of papers, actually, including one that we did recently, detecting fibers in some star-forming regions, and those are actually quite cool. So at fiber level, you start to see a lot of fragmentation. Okay, for prestellar cores, unfortunately, these are extremely small in size. They're 0.1 parsec, typically very cold. So you need certain kind of millimeter instruments to detect them. And they're very, very elusive. I can tell you we have probably less than 2 dozens of known prestellar cores, prestellar massive cores. However, in 2024, in 2024, there were quite a number of, for those of you who know about ALMA, I think from the last 5 years, they've been inviting large projects that are very impactful. So large proposals were being welcomed by ALMA, and there is this large project to observe hundreds of massive star forming regions in different projects. So in this case, for the case of G34.43, in one of our large projects, in this paper that I co-authored with Mai et al., we found probably three new prestellar cores. And one way you would know, this is called the millimeter one. just means millimeter one object. And the contours, the contour and the background are dust continuum emission. And you can see MM1E. This is the band 3. And the other image is the band 6. So, oh, sorry. Okay, so that's the band, these two are band 3 image, and that's the band 6. The frequency is just higher here, therefore you have higher resolution. So what you see as a single core in MM1E is actually here almost resolved as two components. There is MM1E and there is one unresolved core next to it. So this lends to the fact that I have stated earlier that massive stars form in close proximity to each other. Just within millimeter one object, you have the main core A, B, up to F, and in E, there is now E1, and there is E2. In E1, there might be E1A and E1B, if you look carefully. So that's what happens. These things fragment, okay, within the filament. But what is interesting about MM1E1 and MM1C, which is resolved into C1 and C2, is that if you look at the spectra, if you put an ellipse over the continuum and extract the spectra associated with these three objects, you tend to find almost no molecular line, except N2D+, okay, which is likely a hole. And also the SO and CS you see might just be due to emission from other objects nearby. And I can prove that if you perform a beam average spectra for the band 6 data over MM1C1, C2, and MM1E1. This is the spectra you obtain, which almost is devoid of line. And there is also no absorption feature that you can find here. The presence of an absorption feature will imply that there is a warm or hot continuum background source, which will be the protostar, but in this case, there is none. And this is a confirmation that this is a prestellar core, and this paper was accepted in APJ Letters and was published last year. So yes, they are elusive, but we do catch some of them because this phase probably lasts only a couple of decades or a couple of years to a couple of decades, and then it becomes a hot core. So it's an elusive state, but we're happy to be catching new ones. Okay, then you get into hot core phase. I would try to combine hot cores and go slowly into hypercompact H2 region, but I'll spend a lot of time in this state because there are a lot of pieces of the puzzle lying here on how these stars evolve. You go from prestellar core, the core warms up, and now the warming up leads to warming up of the dust, and then the gases are evaporated, and now you can detect molecular line. Of course, you can also start to form masers because now you have energetic photon, you have outflow activities that could lead to collision, energetic photons that could generate radiatively pumped masers as well. So yes, so here's one example. This was done by my postdoc, Jude. This is a case of G358. In this image here, the background represents this pizza image. You can see there is some infrared brightness from this pizza, though quite faint for MM1. But the cyan contour here represents meerkat L-band image. This is likely free emission coming from MM2. And the white contour is a dust continuum image from ALMA. And this is just showing you where the dust condensations are. And you can see how well fragmented you can find multiple components in this. Again, lending to the statement that they form in close proximity to each other. Now, if you look at the chemistry of this object, you can already tell that MM1 is a hot core. This object is very strange because we could find a hot core in MM1, but in MM2, where we already have H2 region, lots of the molecules that we find in MM1A does not exist in MM2. So two things, it could be that this source is already so well evolved and so hot that it has dissociated some of these molecules and you don't detect them. Or that this might be, the free emission might be a background source that just somehow is coincident with the position of the source. We don't have good enough sensitivity. This was extremely faint. I think the peak of this source was 60 microjansky per beam. So you only require MIACA to detect such faint emission. So there's no extragalactic source, so it might be associated with this. It might be a very ultra-compact H2 region, but we find less molecules. Still a hot core, but seems warmer than MM1, which is a bit strange. So I'm highlighting one more problem we have. The more we think we understand massive stars, the more we completely realize that they produce more questions, like why would an object that is already warm enough to produce H2 region have less molecule than one that has no H2 region? That is an open question. We don't know. And the answer could lie on whether this is really associated with this massive protostar. And this also has fainter dust emission, so it could be evolutionary stage, we don't yet know. But we can see evidence of hot core. If you use some of the molecules, reconstruct moment 1 maps, which is the velocity field, like in this case, using this methanol transition, you'll find evidence of rotation. So the contours here is a dust continuum for MM1A, and the lines here show the direction we see the outflow from the carbon monoxide that is detected in this object. And this methanol is showing that there is a structure rotating. We cannot say we resolved the disk yet, but there is a rotating envelope around the protostar. Okay, now I'll move one step to something else. Remember, I said I will talk about lines, I will talk about continuum, I will also try to talk about mesas. And in each piece of the puzzle, I'll be making reference to different star-forming regions because nobody has lived 1 million years to trace the beginning of one massive star-forming region to the end of it. So we can only pick different evolutionary stages and different activities from different objects, and we piece the puzzle together to form a global picture of how we understand this star forming region. I like this source a lot. I almost never talk about star formation without speaking about it. And the reason is because Cepheus A was a pet source to Chema. I don't know if some of you know him from Spain. He was a very good friend. And I still remember my first paper was on Cepheus A, and he was a co-author in it, and he's such a nice person, retired recently. His name is Jose Maria Torres. So this is the result he published in 2011. The distance to this source, oh, sorry, I said 600 before, but it's 700 parsecs. And with VLA, they've shown that it has 14 radio continuum sources, and there's a lot of water mesa activities. And that's the image you have here. The contours here represent the 1.3 centimeter VLA continuum taken in 1995. And the star and crosses are mesa spots or mesa emissions from this source. The color represents the local standard of rest velocities. And if it's a star, if it's a cross, is VLA. If it's a asterisk, is VLBA from 2001 to 2002. If it's a star, is VLBA from 1996. So all these combined just to give you a global picture of how the distribution of the mesas are. And each mesa cluster is labeled with region 1 to 3, 4, 5, 6, 7, 8, and there is HW3D and HW3C. Okay, so I want to show you one beautiful example of a jet and what a jet could do to mesa emission and mesa kinematics. This white contour lines, which is elongated, is actually a known jet in this famous object called HW2. By the way, HW is Hugh and Waterloo, the first people who observed the source and labeled the names. So this jet has been observed multiple times with VLA, therefore they can measure the shift in the peak of the knots and compute the proper motion of this jet. And it corresponds to about close to 500 kilometers per second. So you have a jet launched in this direction. There is a disk in this direction, and there is this water mesa. Now, you see these mesas were discovered only in 2001 to 2002 observation because they are in asterisk group, arrow 6, arrow 7, arrow 8. And now you have a jet moving in this direction. So imagine you're close to a trend line or bullet train, fast moving trend line. The closer you are to the trend line, if the speed trend crosses, the more the gush of wind you feel. The further away you are, you still feel something, but the gush of wind is now much slower, so the effect is less on you. That's what you see here. So in arrow 7, okay, we see significant motion, more than 5 times what the others are doing. Okay, so it's about 70 kilometers per second. We see it moving in that direction. This is because if you draw the axis of the jet, arrow 7 mesas are excited closer to the axis. But what is even more interesting is that you see that arrow 6 and arrow 8 are also moving away. So you have this nice wide opening angle that Chema found, which was very interesting. And I was doing PhD with mesas. I found this so fascinating. So you find a collimated jet, and the impact of the jet could lead to wide angle wind or wide angle outflow, which you can compute the opening angle to be up to 102 degrees based on the mesa kinematics, which is extremely cool. So based on this, I decided, okay, why don't I go look at this object, since we have the Vera project. It's a VLBI instrument in Japan with which I could observe this source multiple times, at least use the archival data. But first of all, I went back to the VLA archive, made image that I found the data, archival data of the same source with the same observation setup. And then I made the image. Everything else, HW2 looks the same. HW3C still looks compact and the same. The contour levels are just different, but HW3D has significantly changed. In fact, the cross I put in here corresponds to the peak position of this compact emission. The peak is now here, and the continuum source is now elongated. So that was a huge red flag. Something is definitely going on in this object. It's either that this object, the entire object, is an ionized jet that is traveling. It's now elongated, or that the core here still exists there, but there is a secondary core. There is multiplicity in this object that we just don't resolve with VLA. The other option is that this is a fast-moving source, but this is a less plausible option. We know a star to move in very few 1 or 2 or 3 kilometers per second by itself, not the gas around it, the star itself moving. They typically don't have high proper motions. But if we consider this to be moving, the proper motion over 10 years, we can compute that to be 65 kilometers per second, which is very ridiculous, fairly unbelievable. So There's also flux variation. The flux density between the 10 years changed by almost 3 millijansky, which is also something to consider. So since VLA cannot answer our equation, we refer to the masers. And I have used here this is my first paper which Chema was part of during my PhD. So that is where the distribution of the maser spots, the colors still represent the local standard of rest velocities, because these masers are observed in multiple epochs. So you can put in the position in one epoch, compare it to the next one, compare it to the next one, and then calculate the velocity, the proper motion in terms of velocity and direction. Okay, so these vector lines are the proper motions from maser spots. Each of these is actually a cluster of spots calculated from this, detected in observation. And if it's broken line, it just means that the proper motion was computed with three or less epochs of the observation. And if it's solid line, it's more than 3. So what you see is there is this northwest and southeast masers are pointing outward from what I consider the C, the central region, which is nice. It's just showing us that there is a bipolar outflow. So if you imagine that the central star is here, which is very likely, the velocity gradient we see a gradient going from -21 kilometers per second up to 0 because there is a red component there. So this is evidence of turbulence around the central region. But if things are moving outward, you expect motions to go outward. But we find this pointing backwards towards the central source. So using what I call expanding flow model, I showed evidence that there is multiplicity of objects in this region, which is cool. Okay, just in the last few days, on the 11th of Feb, the methanol masers in this object has been reported to be flaring, and I consider this a good time to revisit this object again. With that flaring, I would like to come to what we call accretion burst. This is how we currently, this is the knowledge from the last 5-6 years. This is how massive stars gain their mass. We don't think any other theories maybe they could play a role, but the most plausible solution to having a star in main sequence to continue to accrete material is that the disk will add such accretion in episodic form. And I will explain what all that means. So in 2016, Garatti stumbled into this observation where this is infrared observation. You can find S255 here, which has been observed in 2009. And by 2015, they conducted another observation with panic in the same KS band and found this SS emission, which is completely different from this. This part is only showing how the cavity walls of the outflow has changed between these two. So this is the first ever known accretion burst in massive star forming region. And as you can see, it's less than 10 years old. That's the first one that was reported in Nature Physics, which is nice. And that led to models being made using the information obtained from some of the observation to say that to grow the mass of massive stars, you need these multiple episodic accretion events that are that have very high accretion rates. Like you can see, every of this spike shows the accretion rate increasing. In fact, some of the accretion bursts can, within a short period, have accretion rate up to close to 1 solar mass per year, or at least half a solar mass per year for a short period of time. So this means that massive stars they grow by short periods where they swallow up a lot of materials, and then everything goes completely crazy. And then it comes back down to fairly quiescent phase for some time, and then it flares again and flares multiple times. This is similar to what you see in low mass stars. I think they call it The low mass community call it FU Orionis and XORs. We're seeing many more of this. The second example was the NGC that I told you, NGC 6334. I measured the distance to these objects in 2014 to be 1.3 kiloparsecs. And we had a coincidence. We've been monitoring the masers. The maser transitions are named here with Hubble telescope, and this flared. By flaring, I mean the flux densities of the masers just grew significantly larger. We were fortunate in this. The hunter and the wife were also, they conducted ALMA observation of this around this time. This was not planned. It was just a mere coincidence. This is the observation from ALMA here. And there has been previous observation of the same source with SMA in 2008. So we see a brightening here, but of course, this is ALMA with a different kind of beam than the SMA beam. So what you can do is to take the visibilities from the ALMA observation, convolve it with SMA beam, and then you produce this image, which is similar to this. You can simulate this, the SMA observation with this data. You'll still produce the same kind of image. Then you subtract the previous SMA observation from this, you'll get this SS emission. These other three sources still look alike, but that guy has significantly increased. That's what you see here, that somehow the dust temperatures will increase. Okay? You will find the luminosity increasing, which is cool. So we cut this object. We actually calculated the accretion rates and how much mass it accreted. I'll show one last example. This is just an animation to show you how we know we set up what we call a maser monitoring organization, where all the single dish, almost all the single dish telescopes on Earth participate in monitoring masers, and each one that finds a maser going from what the fluxes were to something significantly larger reports back to the organization, and we trigger follow-up observations with VLA or EVN or ALMA and everything. And this one was spectacular. When this flared, we saw from the beginning of the flare, we cut it in the start and we went quickly to ALMA. We detected 14 new transitions of masers, millimeter masers that has never been seen before. Some of them were torsionally excited masers. The dust continuum looked like this, and the flaring source is the MM1 here, and had very interesting velocity coherent maser structure within the object, which is quite cool. So it means that within star-forming regions, there are activities that bring out some physics that we still do not know. For example, these maser transitions that we have never detected, that we're yet to understand the physics of how they are excited. We have detected some, of course, they are very transient. They happen within, some of them within 2 weeks, and then they disappear, some of them within a few months, and then they go away. So we still need to understand physics of some of these transient processes, which is still a gap in our knowledge. Okay, so I need to be quicker now. I move to the ultra-compact H2 regions. In this case, I will introduce a project that we've been doing with the Meerkat telescope. Meerkat is a centimeter band, but it's super sensitive. You go down to 4 microjanskis per beam sensitivity. So it means if anything is 12 microjanskis, you can potentially detect it if of course, that patch of the sky has less noise. The resolution is not great, but 7 arcseconds is still good enough. And we've mapped the entire galactic plane. Don't worry about the galactic center. It has been mapped by a different group, and the data is available for everyone's use already online. So with this, we're hunting for H2 regions now to say, hey, how many H2 regions, how many star-forming regions that we don't know are deeply embedded in their clouds, and we have no idea that they exist. And we're finding tons of them. Of course, first, we have reconfirmed all the known H2 regions reported with infrared. And we're finding a lot more new ones like this A and C, were never reported or detected in radio continuum before. And then we were showing that there is a hypercompact H2 region here. There is also one in this object, which some of my students are working on. Okay, so for OB association, there is not much to say there. If you do, I know many of you know much more about blue stars than I do. I don't do a lot of optical observation, but this is some of the astrophotography of Orion that I have seen. And all these blue dots are part of this Orion trapezium, which I think is super cool, and is an OB cluster. Okay, so as a bonus, here is what we know. Let's say you've got your massive star, you've traced the evolutionary sequence, you get to the time. Of course, it's shining. If it's shining already, just get ready, it will die soon. Of course, it's not in the time scale of 100 years that correspond to our lifetime. It might still be a couple of tens of thousands of years before you see a supernova explosion. But when they're about to die, this is typically what you will have. It goes into super red giant, and then it explodes. Okay. And whatever is left, this explosion would essentially accelerate particles and generate loss of synchrotron emission. And there are so many supernova remnants that have been detected. And these are some of the examples. Well, they've been observed with other telescopes that are not so sensitive. With MeerKAT, we are seeing a lot more structures. Now you can go back to simulations and add a few more information to generate some of these nice, well-resolved structures and morphologies and tiny filaments that we see coming from this blast, which is super cool. But what is more is that we are visiting the sensors of supernova remnants in our Milky Way. For example, this is Spitzer composite image. If I asked all of you to guess if there is a supernova remnant here or not, you will most likely say no. But here's what the MeerKAT observation looks like. Absolutely spot on that there is a new supernova remnant hiding here. It may have been old, and the surface brightness of the synchrotron emission is now very low, but with the sensitivity we have, we can still clearly show that there is supernova remnant. It's not just that one, there is this one. I'm showing you the infrared and as well as the MeerKAT radio emission. There's that one, there's that one. You might think the one that dropped previously is just H2 regions, but no, there is a supernova remnant lying there. And you might actually be seeing triggered star formation in that region. This is one, and there's that one. Okay, I think I have spoken quite too long. I hope you've seen a bit of the evolutionary sequence of how the big stars that you study, how they are formed, or the massive stars, how they are formed. We don't think we have all the pieces of the puzzles yet. We keep searching. The more we find, the more we are able to tell you. And I hope you stay tuned and hear more about it in the next 5 to 10 years about what new puzzle piece that we have. Thank you very much.
Thank you very much, James, for this very comprehensive description of how can be the evolutionary sequence of massive star formation. Now it's time for questions. Is there anyone wanted to ask? If not, or while people is thinking about this question, I have, I'm not expert at all on this, and we were actually discussing this before this started, if people were going to ask or not. So I can ask you some basic question, and maybe you know, maybe not, but it's something that I normally hear when I listen to things related to star formation, massive star formation. One of the things you say is that the massive star continue to accrete even after commencing the hydrogen fusion. Is this something that there are observational evidences for that, or is something that?
Yes, Cepheus AHW2, for example, the one I showed that has a jet, you can already see in infrared. It does have a disk, and we observe molecules within the disk, and we still see what we call P-Cygni profile in some of the molecular line. And P-Cygni profile is evidence of infall. So there is still infalling of material both into the disk and from the disk into the protostar. But this star is already in main sequence stage.
Okay, and how you know, this is curiosity, how you know that the star is on the main sequence already? So what is the...
Okay, so you can plot the Cepheus A already have infrared luminosity. You can plot plot it on the HR diagram, and you find it right in main sequence.
This is the location in a diagram.
Yeah.
There is still no question. The other thing that I was thinking when you were presenting things is, in many cases you were talking relating for example, the prestellar core, and you say that there is a massive star inside. But how you know, is there a way to measure masses in this prestellar cores, or how is it done?
Yeah. So we have what we call the dust to gas mass ratio. So if we know how much dust you have from measuring the intensities of the dust emission, then we use the ratio to convert the gas. Okay. So the gas that is still frozen onto the grain, but we can tell you that the mass should be this range. So we use the dust to gas mass ratio to extrapolate and get the masses.
Okay, and what is the range of masses that we are talking about in these cases?
They go 12 to sometimes 70, 100 solar masses, depending on how big the clump is.
Okay.
Yeah, so they are massive. They are definitely above 8 solar masses.
Any question by there is Naval, so please ask.
Hello, Professor James. Thank you very much for the such a nice talk. Actually, I have a question connecting to the question which just asked by Professor Sergio. Actually, I was wondering, how do you define this massive crystallar core? Like, what is the mass, like minimum mass you define for core to be massive crystallar? Because you showed in one of your slides, there are some new massive like crystallar cores you showed that where the dust continuum emission is present, but there is no such gas emission.
Yes.
So
let me see if I find. I think I have that paper open somewhere. No, I don't. But I can tell you what the masses of that prestellar core were. With band 3 data on the 2 prestellar cores. You remember in the band 3, it's not resolved. Let me go back to my slide. That would be quicker. There. So in the band 3 image, it's just one core, okay? If you take this as the composite core and you use the dust to gas ratio to compute the mass, this is over 20 solar masses, and that is close to 70 solar masses.
Oh, okay.
So we know they are massive, but then there is no gas on the dust condensation. So protostars must have both the dust and the gas peaking on the peak of the dust emission. Then that means that there is a background source that is already warm enough to release the gas on the dust grains.
Mm-hmm. But in that way, like some theories suggest that the massive like crystallar core doesn't exist, and once those massive dense cores host like low mass protostar, but then it accretes material from the parent envelope or the clump, and then it forms the massive protostar later. What is your views on that part?
So when I was doing PhD, there were about 3 competing theories. There is the disk-headed accretion theory, which at the time wasn't popular. And there is also this what you mentioned now was called at the time competitive accretion, where you form lots of small low mass cores, and then they compete for the material around, and accrete them. And the ones that are closer to the systemic velocity of the cloud will accrete more and have more chance of growing into a massive star. Competitive accretion, with ALMA coming on board and producing lots of this fantastic image, there is still competition to accrete material, but we think the disk is the most plausible one for growing. Having a disk-headed accretion is the most plausible one for growing massive stars. Remember also, there is also the coalescence theory, where they said all the many cores in low mass phase form, and at some point they come together and combine and become massive. We haven't seen any one of those any source supporting this. The theory may be correct, but we don't have any clear observational proof of merging low mass stars to form high mass stars, except you're in low mass community and maybe you can show me. I have not seen any one of those papers. So yes, in terms of theory, there were lots of things that were said, but everybody in the massive star formation community is now focused on disk-headed accretion, because that's what the data we're getting now seems to support.
Okay, thank you very much. Thank you very much again for such an exciting talk.
Thank you.
Okay, so maybe we can have the last question by Debbie.
Hi. Can you hear me okay? Yeah. Good.
Yes.
Thank you for a very nice talk. About multiplicity, you talked briefly on it, but forming in multiples, I don't have a sense of how less massive stars form in contrast to this. Can you talk about why binaries are more likely to form in more massive stars?
Yeah, I didn't talk about binaries, because that's a whole maybe 1 or 2 hour talk. We have binary systems in high mass stars. Actually, we have theories proposing that the behavior we see in some of the masers is as a result of binary systems, collision of the winds of a binary system, but I didn't venture into that because of time. However, comparing this to low mass stars, maybe because low mass stars, you can find a lot of them closer to us, you can actually identify one and focus on that, and you have no complex environment where you have complexity like the outflow of this interacting with the outflow of that. There may be small instances, but in the case of low mass stars, you don't find this lots of clustering that we see in high mass stars. It's difficult to go into any massive star forming region, take 1 arcsecond by 1 arcsecond region and not find up to 10 protostars, massive protostars in it. It's fairly difficult. There are a few examples, but it's not very common. So that's what I mean by the multiplicity. Of course, there is some level of multiplicity in low mass stars, but you can always find formation in some isolations that you can, take on the side and then deal with, but you can't do that for high mass stars. If we plot, for example, the gas motion of this region, it becomes so complex because outflowing material coming out of this will be interacting with outflowing materials from this, and it makes a complete mess that identifying, isolating the feedbacks becomes literally impossible. Yeah.
Great. Thank you.
Yeah, sure.
Okay, so I think it's time to close the gathering for today. So thank you very much, everybody, for joining us, and thank you once more, James, for this very interesting presentation. And hope to see you soon, everybody.
Thank you very much, Sergio, and thanks everyone.